Hello and welcome to the very first episode on this channel. My name is Chanakya and I am an A-level student who recently completed my A-levels in 2025, and I thought I'd make some of these videos to help my friends and other people who want to learn this syllabus. So yeah, enjoy the video. I was thinking about making a video like this in single medium, like a single medium version of this video. If any of you would be interested in that, comment down below. I might make it potentially. And also this is going to be only the math syllabus on this channel. If you want chemistry and physics, go ahead and ask down in the comments again. I'm planning on only doing maths, but if you want, I will do those as well. So let's begin and talk about the very first lesson I'm going to talk about today, which is sets. Alright, so we're going to begin today with the lesson of sets. The lesson of sets. So first we're going to have to talk about what a set is. A set is a collection of stuff. Set is a collection of different, unique, well, we'll just say things for now. So it doesn't really matter what the set has. It can be literally anything, and there's no real limitation to what you put in a set. For example, the set 1, 2, 3, 4 is valid. So is the set of an apple, let's say a banana, let's say Earth, and let's say the International Space Station. This is also a set. This is also a valid set. So here I want to drive home the point that it doesn't matter what you put in the set. We can even put a 3 here also. Any collection of different elements can be considered a set. So you might wonder why we're talking about this as the very first lesson today. And that's because sets are actually quite important. In fact, numbers in the modern times are actually defined based on sets. We'll not go into how that's done, but sets are quite important. So let's begin. Before we can actually talk about using these sets, we need to understand how we can represent them, what the notations are. So we're going to start with notations of sets. So one notation of sets is to simply use capital letters. It's very common to do this. So capital letters, like let's say we could put A, capital B, capital C, capital D, so on for the different sets. We could also use special symbols. So let's say special symbols like, for example, actually it doesn't really matter exactly. You can even put some crazy symbol like this. Some things that are practically used is this. Let's say this is a special symbol that's used in sets. So is this one. So is this one. And so are a bunch of others. So we can put some symbol to represent a set. Usually it's a capital symbol or a large symbol. And next, now that we have the notation for these sets, let's discuss how we write them. So for writing a set, you can, well, the most common way is to simply write the set symbol, like let's say A, say equals, and then describe the set. So here I could say A is the set of symbol A, B, C, D, E, and so on. So this is one way to write out a set. There are others which we will discuss later, but right now this is how you write a set generally. And here it's important for me to clarify what these are. In the nomenclature, these are called elements of the set. So here A, B, C, D, E, and so on are elements of the set A. This is the nomenclature. A, B, C, D, these small little things are elements of the set A. We write this in a special format as well. We say that A is an element of the capital letter A or the set A. Similarly, B is an element of the set A, like this. So what this symbol means is essentially you read it as this symbol is an element of. So here on the left side, whatever we have on the left side is an element of whatever we have on the right side. So similarly, if we have a symbol that's not inside our set, let's say the set ends here, this set A ends here, and all we have is these 5 symbols, 5 elements, A, B, C, D, and E. If we take F, we can clearly see F is not an element of A. So the way we write this is to write F is not an element of A. So here in this case, this symbol represents not an element of. So I could say that this symbol means not an element of. These symbols, these two in particular, will be quite useful and quite important, and they occur a lot, especially in the papers. In papers, they always give certain variables as being elements of certain sets, so that they give it such that it limits the possible answers that you can give, often to just one answer. And in mathematics also, generally, we want to limit the number of possible answers, or we are interested in particular set of answers. So because of that, these two symbols are quite commonly observable in both papers and common mathematics. This is of course more observable than this one, because generally we want an element to be an element of a set rather than not an element of a set. But these two are quite common. So I'll even put a star around this, because these two are quite common definitions and very often used. Another set of, here I use the word set again, another set of symbols are the operators. The operators on different sets. So there's a bunch of operators here. I'll just list them out first. I'll list 2 of them out. Maybe 3. We'll list 3 of them out. So these 3 operators are commonly used in sets. The first operator is the union operator. The second operator is the intercept operator. And the third symbol is the difference operator. So these 3 have special properties and special behaviors that we need to understand when we talk about sets. So to explain these, I'll give 2 example sets. Let's say that A is the set of, let's say, P, Q, R, S, T. And let's say that B is the set Q, T, U, V, W, X, for example. So in this case, what we mean by A union B is all the elements in A plus all the elements in B and cancelling out any repeated elements. So in this case, P has to go in, Q has to go in, but notice here Q is repeated, but that doesn't matter for us. We just cut out the repeated values because we only want the unique elements within the set. So we just write Q. Next, R is an element of the set of A union B. S is an element, T is an element, U is an element, V is an element, W is an element, and X is an element. Notice again, even though T was repeated, it doesn't matter for us because when we take the union, we only want the unique set of elements. So this is what we mean by A union B. Similarly, what we mean by A intersect B is all the elements in A and B that are there in both A and B. So in this case, what we want to do, check if any elements in A are also in B, and then check if any elements in B are also in A. In this case, P is not in B, so P is not in the set of A intersect B. However, Q is in the set of A intersect B, therefore Q has to be in this set, comma, R. R is not in B, so that's not an element. S. S is also not in B. That's not an element. But T. T can be found in B as well. So therefore, T is an element of the set A intersect B. What about anything else? Can we see any other symbols? Here Q we already checked. T we already checked. U is not in here. V is also not in here. W is not in here. And X is not in here. So none of these are elements of the set A intersect B. So the only elements of the set A intersect B are in fact the two symbols Q and T. So Q and T are the only elements of A intersect B. The next one is a little bit different because it depends on the order. The order of these two matters. So this is basically the difference of A with respect to B. So what we do here, we check all the elements in A and we make sure they are not in B. If they are not in B, they go into the set A difference of B. If they are in B, they do not go into the set. So let's take P. P is not in B, therefore P is an element of the difference of A with respect to B. However, Q is in B, therefore it does not go into the difference of A with respect to B. R is not in B, so therefore it goes into the difference of A and B, A with respect to B. S is not in B, that also goes into the difference of A and B, A with respect to B. However, T is in B, therefore it does not go into the difference of A and B, and we've run out of elements in A, so this is the difference of A relative to B. You'll notice if you try to do difference of B relative to A, we get a different set. We'll actually compute that right now. If we look at Q, Q is in here. Therefore, Q is not an element of the set difference of A relative to B. So B relative to A. If you take T, T is also in A. So T is also not an element of the difference of B relative to A. U is not in A. Therefore, it is also an element of this set. If you take V, V cannot be found here. V is also an element of the difference of B relative to A. W is also an element and X is also an element because W and X are also not in A. So you will notice that here, difference of A to B is not the same as the difference of B to A. They are in fact different sets, so you cannot swap that around. So I hope you understood these three operations. There are other operations, but we will not think about them for now. Right now, just understand these three operations. Generally also, we do not use the third operation in the papers anyway, but these two operations are seen in papers. So make a note of that. And next, I would like to talk about some set comparisons. Comparing sets. So we have symbols for this also when you want to compare two sets. Again, we'll continue to use the two sets A and B. And then we'll also define third set C. So I'm going to call C, let's say, what do you call, we'll call C QR and we'll call D UV. We'll say that C is the set QR and D is the set of, suppose we'll say UV. U, comma V. So here, there are certain operations we can use to compare these sets. If you take A, we can see that all the elements in C are inside A. The element Q in C can be found inside A, and the element R in C can be found inside A. So given this property, we say that C is a subset of A. And the notation for this is to say that C is a subset of A. So here, what this symbol is not exactly like a C, it's more of a sideways U and this thing. This means that is subset of. So you'll notice there's also a little equal sign like thing here because we are also accounting for the possible case when C is exactly equal to A. So the statement that A is a subset of A is also valid because A is equal to A, and therefore all the elements in A are also in A. If we know that C is smaller than A, but C also, all the elements in C are also contained within A, then we can write that C is a proper subset of A. Now, again, this symbol is not exactly a C. It is like a sideways U. I'll try to draw it a little bit more distinctly to make sure you can see it is not the same thing. Like that. So what this means is that C is a proper subset of A, which is meaning that all the elements in C are found within A, but C is smaller than A. So we say C is a proper subset of A. Subset of A. Furthermore, comparing D is also found within B. So D is a subset of B. You can see D contains U and V as we defined it down here, and U is inside of B, V is defined inside of B, so D is a subset of B. And also because D is smaller than B, D is also a proper subset of B. However, if you take D and compare it with A, we can see that none of the elements in D are inside of A. Similarly, if we take C, Q is inside B, but R is not inside B. So C is not a subset of B. So the way we write this is to say that D is not a subset. So not that symbol, this symbol. D is not a subset of A, and similarly we could also say that C is not a subset of B. So what this means is that we do not have the condition that all the elements in D are found within A, which in fact is true. This is not found in A. Similarly, this is not found in A. And also the second statement, I said that C is not a subset of B. Even though Q is found in B, R is not found in B. So because of this condition, C is not a subset of B. So these are another two set of symbols. We can put a few stars here. These are not really all that common in papers, but it is important to know them. This symbol, this symbol, this symbol, and well, I mean, these two are basically the same thing. So let's not put a star for this one. So now that we've covered the basics, let's go to some actual sets, some things that are practically used. So I'm not going to go into set theory in this video because, well, we don't really have that in our A level, so we don't need to do it. So I'm actually only going to talk about the sets that we need for the exams. So one set that's required is this. Sometimes the line is a little shorter. This is the empty set or the null set. This is basically the set that contains 0 elements. It is a form of identity set. In sets, it's a very special one. It's the set that contains nothing. So it's special. Then, in practice, in our syllabus, we use some numbers. And in these numbers, we classify them based on their properties. And these different sets of numbers have special names. So in the early days, what we would have done to start counting was to simply count 1, 2, 3, 4, and so on. So in that form of counting, we start from 1 and we count upward in units of 1. So those numbers, the numbers that you can make by starting from 1 and adding 1 each time, are what we call the natural numbers, represented by a capital N with an extra line in the middle, like this. So these are the natural numbers, and the set of natural numbers is defined as 1 plus 1 plus 1 and so on. So 1, 2, 3, 4, 5, and all the numbers such that like that. Start from 1 and then go plus 1 each time. But this set is limited. You'll notice there's not even a 0 in this set. So we cannot represent 0 within this set. There's also no negative numbers, no fractions, nothing. So this is one of the smallest sets of numbers that we can start with as our constructables, like what we can produce. The next biggest set of numbers that we can make, well, it's not exactly the next biggest set of numbers, but it is generally the next set of numbers that we consider. It is the integers, represented by z with two lines in the middle. So these numbers are the numbers as, I'm going to put a bracket open like this. From 0, we can count upward in units of 1. So 1, 2, 3, 4, and so on. And from 0 also, we can count downward in units of 1, of -1, -2, -3, -4, and so on in that direction as well. So these are the integers. And also now that we have the integers, we tend to also have a couple subsets of the integers as well. One subset of the integers is the positive integers, which we write as z with a plus mark up here. So this set is all the positive numbers within the integers, which is, if you count with me, 1, 2, 3, 4, and so on. So this does not include 0, by the way, as 0 is neither positive nor negative. And you might notice, right? You might notice that the positive integers are exactly equal to the natural numbers. And yes, you're correct. That is exactly the case. The two are equal to each other. But we tend to use the positive integer notation rather than the natural number notation in the papers, at least. So yeah, but note that they are exactly the same. So if someone gives you the natural numbers, it's the exact same as saying the positive integers. Furthermore, we have the negative integers, which, I mean, no real explanation needed there. It's just -1, -2, -3, -4, and so on in that pattern also. And sometimes we also have the positive integers including 0, like things like that. So we sometimes write like plus, and then at the bottom a 0. This means all the positive integers including the number 0. So it's a little extra. It's a superset of z plus and a subset of z. It is 0, 1, 2, 3, and 4, and ... So, I mean, sometimes in some applications, some questions, it is required to have this. Sometimes we might write this as the set z plus union the set of just 0 like this. We might write this, but it is often more convenient, instead of writing this, to just write a 0 at the bottom and call it a day. So we have this set. This set is expansive, larger than the natural number set. It contains more numbers. But it is not still sufficient for some things. For example, if I want a half, I cannot show a half within this set. There is no half within this set. There is no √2 within this set. Or the next largest set we are going to construct cannot have √2 within it. We cannot have, let's say, -3/8. You'll notice all of these numbers I'm writing are written as fractions. And those fractions are not available within the set of integers. So the next bigger set expands beyond these integers by introducing the ability to divide. So what we do for this next set, which is called the rational numbers, and often written with a Q with a little extra line on the left, sometimes there's extra line on the right side also. I'll just keep the line on the left side only. This is the set of all numbers that can be written as sum A divided by sum B for A and B within the integers. So we build up this new set from the integers. Starting from the integers, we take two integers, divide one by the other, and use that to construct all the rational numbers. So now, with those, we have this extra ability. This set now contains numbers that were not available in the integers. Specifically, all the fractions are now contained within the set Q, the set of rational numbers. However, there are still some other numbers which cannot be represented within this set. For example, what I brought up earlier, the square root of 2. The square root of 2 cannot be written as a divided by b for some ab in the integers. And actually we could prove this. There's a proof by contradiction. I might create a extra video, in which case it'll be linked up in the top right as to a proof of how root 2 is irrational. I'm going to use the classic proof by contradiction method, saying that assume that the root 2 can be written as a divided by b for some integers a, b, and then show that there's a contradiction in that both a and b need a common factor. This is the set Q containing all numbers that can be written as a divided by b for some integer a and b. This does not contain numbers like root 2, and for those numbers we add this. This is the set of real numbers, often written with a capital R with an extra line on the left side. The set of real numbers has multiple definitions, but it's basically, you can think like it's any number that can be written as an infinite or finite decimal. There's another way to say it, saying that any real number can be constructed by an infinite or finite sum of rational numbers. So this thing is, let's say, all numbers that can, well, I'm not going to give you the exact definition, because this is not the definition, by the way. Do not write this as a definition of the real numbers, because it's not the definition of the real numbers. All numbers that can be written as a finite or infinite decimal expansion. This is not the exact definition, I repeat, but this is good enough. So the real numbers was for a long time one of the largest sets. In fact, you could consider it to be the largest set within all of these numbers. But there are numbers that do not exist within this set. For example, now here this has to do with Euler and that era of mathematics. Consider the equation x squared plus 1 equals 0. Can you find any real number, any number that can be written as a decimal expansion that will satisfy this equation? For any positive number, let's say if x is 1. If x is 1, then x squared is 1 and 1 plus 1 is 2, not equal to 0. If you instead put x is negative 1, then you still get x squared is 1, which then still means that 1 plus 1 is 2 and not 0. So again we seem to have no solutions. We could try even harder, or we could simply use some algebraic rearranging and figure out that x squared has to be negative 1, which doesn't exist for the real numbers, because any positive number times itself is a positive number, and any negative number times itself is also a positive number. You cannot get a number times itself to equal a negative number within the real numbers. So here we find that x is equal to the square root of negative 1, which doesn't make any sense within the normal mathematics. We had to invent a completely new number system in order to explain this, and once we did explain it, we had a huge, let's say, treasure trove of different methods of doing calculations opened up to us by considering the square root of negative 1 to be a proper number. This set of numbers that includes the square root of negative 1 and its multiples is what we call the complex numbers. The complex numbers are represented by a C with a line through it like this. The set of complex numbers is any number written as a plus b times the square root of negative 1 for a element of the real numbers and b element of the real numbers. This is a condition for any complex number. So here I should also mention, before continuing, that the square root of negative 1 is written as I. We consider this the imaginary unit. I is what we call the square root of negative 1. So whenever you see I, probably we will encounter it in a few late lessons. I is the square root of negative 1. Therefore I squared is negative 1. Or you can think like I is the number such that the square of I is negative 1. So we won't get into that right now, and we'll probably get into that a few months later, or maybe maybe not that long even, depending on how often I upload. But I'm going to cut this negative square root of negative 1 thing because I honestly hate that notation. A plus bi, where I is the square root of negative 1. So complex numbers are any number written as a plus bi, where a is a real number and b is a real number. Now I should mention that this is the largest set that we have for our A levels. However, this is not the largest set of numbers. There are other numbers that we could construct that could some possibly be unrepresentable using the complex numbers. We can even define a set of numbers that specifically non-representable by the set of complex numbers. And also within these sets there are other sets of numbers that we have in mathematics. For example, within the real numbers there are something called the algebraic numbers, which are often written as a capital A with a line like this, or sometimes capital R sub A. These numbers are numbers that can be written as solutions to quadratic equations or further equations. Well, quadratic and further higher. Well, let's say just say polynomial equations. Algebraic numbers are the numbers that can be written as solutions to polynomial equations. There are some numbers that cannot be written as solutions to polynomial equations. For example, pi. Pi is what we call a transcendental number, which means it cannot be written as the solution to something of the form ax to the n plus bx to the n minus 1 plus cx to the n minus 2 and so on and so forth until constant term. So yes, we are not going to talk about that because it is not relevant for our syllabus, but note that this is not all that we have in sets. There are many more sets, but this is where we're going to stop. Now that we've talked about the basic ideas of set theory, let's go to defining what a relationship is and what a function is, and that will conclude this lesson. So to describe a relationship, we just have to say we have some set of inputs A. From these inputs an element goes. This element goes through a relationship, and when it comes out it is related to some element of B. So some element of A goes into B. This is basically what a relationship is. Relationship is. Now often this happens two way, as in some element of A is related to B in some way, and that also means that some element of B is related to some element of A in some way. So we could consider this relationship to be a mapping between elements of A to elements of B. There is some way that we can map one and connect it to the other element of the other one. So I'll call this E sub A and E sub B, but these two are correspondent to each other in some way. So here different kinds of relationships can be there. If we're talking about purely mathematical, then the relationships are of course mathematical. If A is the set of 1, 2, 3 and 4, and B is the set of let's say 2, 4, 6, 8, then even to us it's very obvious what the relationship here is. For any element of A, we have doubled it and sent it into B. So here 1 has been doubled and sent into 2, 2 has been doubled and sent into 4, 3 has been doubled and sent into 6, and so on. So here the relationship is element of A times 2 is the corresponding element of B. We could of course have other relationships as well. If we have, say, instead of this set of B, if we have instead 1, 4, 9, 16, now the relationship is that element of A taken and squared is the element of B. But here currently the relationship we have, we can clearly see one element of A maps to only one element of B, and if we take the reverse direction, one element of B maps to only one element of A. This is the simplest kind of and easiest relationship to understand, where it's a one-to-one relationship. One element of A maps to exactly one element of B, and that element of B maps exactly to one element of A. This is of course not always the case. if we consider the set A to be instead of this set, we could consider, say, let's start from -4, -3, -2, -1, 0, 1, 2, 3, and 4. If we consider this set, and if we consider B to be the set 0, 1, 2, you know what, we'll put the squares, it's easy to explain. 4, 9, 16. If this is the set B, and suppose that I said the relationship between A and B is that the value of A squared becomes the value of B, then we can see in this particular case -4 squared maps to 16, but 4 squared also maps to 16. Here also -3 and 3 map to 9, and 0 maps to 0 only, but so that's nice. But the rest of these you can see there is some repetition. -1 squared maps to 1, maps to 1 I should say, and 1 squared also maps to 1. So here we have the case where multiple elements of set A are mapping to single elements of set B. So here if we try in the reverse direction, if we try to map B to A, we can do it for 0. 0 maps to 0, not a problem, there's only one thing it can map to. But if I consider something like 4, 4 could have come from this one, this -2. It could have come from this 2. So we do not know which one it came from. It could have come from multiple. So here, this is a one to many sort of, actually many to one sort of relationship. There are many possible inputs in A that are going to single outputs in B. This is a many to one relationship. Actually here specifically it is a 2 to 1 relationship except for 0, which is a 1 to 1 relationship with itself. So here this is another type of relationship, and if we flip these two around and we try to consider the relationship of B to A, then one value of B maps to multiple values of A. So in that direction it's a many to one relationship. Many elements, 1 to many relationship. One element of B maps to many elements of A. So in this case it is a completely different form of relationship where we have one element mapping to many different elements. Furthermore, if we instead of this one we have something like I don't know, let's erase this and consider another one. Let's say we have, you know what, let's erase both so to make it very easy to understand. I want to give an example where multiple elements of A map to multiple elements of B. So let's do that with this. We'll do -1, -1/2. Actually we'll do -√3 over 2, √3 over 2, -1/2, and then we'll do -1 over √2. Then we'll do 0 after that. We'll do 1 over √2, 1/2. Actually these should be in the other order, but it's alright. Half, and then √3 over 2 and 1. So now considering this set, and let's let B be the exact same set. Alright, let's let B be the exact same set. So I'm going to copy this thing and copy it, paste the exact same thing into here, and say that B is the exact same set as A. So in this case we have a bunch of values in B, bunch of values in A, and suppose I tell you that the relationship between these two is that an element of A squared plus an element of B squared is 1. I suppose I tell you that this is the relationship between certain elements of B and certain elements of A. Then you could, if you consider any element of A, let's say -1/2. -1/2 squared is 1/4. So on this side you would have over here 1/4 plus some element of B squared equals 1. So now what could this element of B be?
Well, we need the element of b squared to be 3 divided by 4 to make this work. But notice there are two numbers that could do this. There's negative 1 over root 3, negative root 3 over 2 and positive root 3 over 2. Both of these numbers would satisfy this condition of 1/4 plus element of b squared is 1. So that means the input of negative 1/2 of a maps to two elements in b, specifically negative root 3 over 2 and root 3 over 2. Similarly, if I consider this one, let's say this element in b has negative 1 over root 2. If we put that into here and substitute, then what we would get is that element of a squared plus, now here negative 1 over root 2 squared is 1 over 2. 1 over 2 is equal to 1, which then means that element of a squared is equal to half. So, what are the possible solutions for this one? Well, again, there's actually two. This is a solution and this is a solution. When you square both of these, you get a half, which works. Negative 1 over root 2 and 1 over root 2 both square to give you half. So here, any input in B is also mapping to multiple inputs in A. Now, there are some functions that do this. For example, one I just gave you does this, and this, because of this, by the definition, which we will get into in a moment, these are actually not functions, and I will explain to you what I mean by function and why these are not functions shortly. So, let's consider the different types of relationships we found so far. We have found relationships such as, give me a second, I want to erase this. We have found relationships such as one element of A going to one element of B. So this is one element of A going to one element of B, and one element of B going to one element of A. So this is what we call a one-to-one relationship. I'll say 1 to 1. We've also had relationships where one element of A goes into multiple elements of B, and multiple different elements of B correspond to a single element A. So in this case, this one is what I called a one-to-many relationship. And I also turned that same relationship around, and then I showed that many inputs of A can go into one input of B, where one input of B goes into many inputs of A. This is a many-to-one relationship, and furthermore, with this last example, I showed you that there are possible relationships where many inputs of A could go to many inputs of B. Now I'm going to explain why I just wrote capital N instead of capital M here real quick. It's because I want to show that this is not necessarily the same number of inputs mapping to the same number of inputs. It's not that one input maps to 2 and 2 inputs map to 1, although in this case that is actually what's happening. I just want to show that it's not 5 inputs mapping into exactly 5 outputs every single time. It is that some number of inputs maps into some other number of inputs. It could be confusing or misleading to write capital M for both of these. So this is a many-to-many relationship. So out of these, the only ones where a single input turned into multiple outputs, but one output could only be found with one input, were this one-to-one one and the many-to-one one. These two produced many outputs from just one input, which means they could not reliably give you one answer and only one answer for one given input. So what I mean by that is, say I input 2 into a certain function. If the function says that, well, 3 is a possible answer but negative 5 is also a possible answer, then in that case there are 2 possible answers and the function cannot tell me which of them is actually the correct answer. There's no such thing as the correct answer there. However, in the first function and the third function, given any input, there was only one correspondent output, which means I knew for sure what that output was. These two relationships are given special names. These two relationships are what we call functions. And sum of these two relationships is what we call a function. So what this means is that a function, in the classical sense, a function is something, some object, an object that maps one input from A into only one input, one output in B. Only one. So that's the important part here. So a function can be either 1 to 1 or many to 1. It cannot be anything to many. That will not work, because that would mean that there are multiple answers for a single question. So an example of such a function would be the function f, which maps x onto x squared. So here, by the way, this is some notation. F is a function which maps x, it maps x onto x squared, is what this means basically. So here, for any x, there is only one answer for x squared. So this is actually a proper function. If I put x equals 1 here, I get 1 here. If I put 2 here, I get 4 here. If I put negative 2 here, I still get 4 here, but this is not a problem, because for one input, I only got one output. So something like, if I said that this function f maps x squared onto x, then we would have a little bit of an issue, because 1 would map then to both 1 and negative 1. Sorry, both, I actually wrote that the wrong way. I wrote negative 1 first. Both 1 and negative 1, which is an issue. We should not have a function mapping one input into multiple outputs. It would also map 4 into 2 and negative 2 at the same time, which is not going to work. So remember, a function is something that maps one input into exactly one output. So we'll end this lesson here by just considering some functions and what they look like on a graph. So let's consider the function I actually talked about in the very beginning, right? I mean, not very beginning, at the very end. The function f that maps x onto x squared. So if you say this is x and this axis represents f of x or x squared, then the graph will look something like this. Given that this is 0, from 0 it will be 0. On the right side it will come up like this. The left side also it will come up like this. So now here in this case you will note that for one value of x there is exactly only one value of y or one value of fx, but for one value of fx there are two values correspondent to x, which is not a problem for us, because we defined a function as something where one input gives only one output, which is valid in this case. From this graph you can clearly see, for any input there is only one output. Compare this to something like a circle. The graph of a circle is not a function, and I'll show that to you right now. Consider this, this is the axes, x and y axes. Consider a circle. A circle would be something like this. So in this case we can see, for any x, I'm going to label these x and y, for any x there are two y values correspondent to it, and for any y value there are two values of x correspondent to it. So here from x's perspective there are multiple values of y for x, which means it's one to many for x, and from y's perspective there are multiple values of x corresponding to it, so it's one to many from y's perspective. So overall for y it is one to many, for x it is one to many, therefore overall the relationship of y and x is many to many. So in this case the graph of the circle clearly shows that the circle is not a function. And I'll tell you another thing. In this thing, the square root, it is true that for one value of fx there are multiple values of x. This is not a problem in the forward direction, because for one value of x there's only one value of fx. However, if we want to find the inverse function of fx, the function that gives the inputs of x, we will find that it is not a function. It is not a function because for any one value of fx there can be multiple values of x. So this is something to note. Just because a function is a proper function and one input maps to only one output, it does not necessarily mean that the inverse function is a valid function. It could be a one-to-many or many-to-many relationship potentially, in which case it would not be valid. In this case, you might think that the inverse function, which I'll call f inverse x, is simply the square root of x. You might think that this is the case. However, this is not valid, as this definition of square root of x only gives us the positive square root of x. In reality, f inverse of x is mapping x to plus or minus square root of x. This is not a function, as there are two values of x, but this is the inverse relationship of the function fx. So I just want to throw that out there. Just because a function is proper does not mean its inverse function is proper. In fact, the only way that a function's inverse function is proper is if the function itself is 1-to-1. Because if it's 1-to-1, then any input A mapping to one input B means that that input B maps only to that output A. So just as an extra side note, if f inverse of x is also a function and f of x is a function, this means that f of x is a 1-to-1 function. And that concludes our lesson for today. We learnt about a lot of things today. We learnt about sets, saying that set can be defined by any capital letter and such that a set is a collection of different items. We also said that to represent a set, the easiest way to do it is say that set equals and all the elements within the set. Or we could also give some rule for the set, such that saying something like A is all the even numbers or something in words also. And furthermore, we talked about the notations for sets, saying that if A is an element of the set capital A, we write it like this. We also said that if, let's say, B is not an element of the set capital A, we write it like this. We also talked about adding two sets together in different ways. We talked about the intercept function, the union function like A union B, A intersect B. We talked about the difference of A and B as difference of A relative to B and difference of B relative to A, and talked about how these two are not equal to each other. Furthermore, we also talked about comparing two sets, saying that if we consider the elements of set A and set B, we could say something like A is a subset of B, which means that all the elements of A are within B. If we know that A is smaller than B, and also the fact that A has all its elements within B, then we could say that A is a proper subset of B. Furthermore, we also talked about the fact that you can write this the other way as well, saying that B is a superset of A, or if we know that all of them are inside, we can also say that B is a proper superset of A. Furthermore, we also talked about the fact that when you consider these elements, there could be the case where it's not a subset or superset, in which case we would just put a cross like this and say that A is not a subset of B, and so on. And finally, we concluded that section by talking about the different sets that we use in common mathematics. We talk about the null set, which is the empty set, which contains no elements within it. We talked about the natural numbers, which is a simple set of numbers starting from 1, 2, 3 and so on. We talked about the integers, which is basically all the whole numbers. And then we talked about the rational numbers, which can be written as a ratio of two integers. Then we expand this thing to talk about the real numbers, which I didn't give the proper definition of because it's not relevant to the syllabus, but if you want, you can find it. Furthermore, I talked about how there's some numbers that cannot be represented within this set of real numbers, which are the complex numbers. Furthermore, I talked about the fact that there are actually other subsets of these numbers that we are not talking about, and there's also potentially supersets of these numbers that cannot be represented by them. And that concluded the lesson on sets. Then finally, as a final part, what we talked about is relationships and functions. In terms of relationships, we talked about relationships that map one element to one element. We talked about relationships that map one element to many elements, relationships that mapped many elements to one element, and relationships that mapped many elements to many elements. And then we talked about how only two of these are considerable as functions. The functions are the ones that map one element to one element and many elements to one element. We talked about the fact that given that a function maps certain elements to certain elements, its inverse function can also be a function if and only if the function itself is a one-to-one function. So if f inverse of x exists as a proper function, then fx is one-to-one, and that concluded the lesson for today. This is some basic knowledge, but this knowledge will be very useful and very important everywhere within the syllabus. In all sorts of papers, in all sorts of questions, you can always see the set notation as a sort of guideline for what kind of numbers you are allowed to use. And so that concludes our video for today. I hope you enjoyed. Thank you for watching. I will be producing more of these videos soon, and we'll be covering the entirety of the math syllabus. If you want, we will cover the chemistry and physics syllabuses as well, but that all depends on demand. I personally really like mathematics, which is why I'm doing this one. So tell me in the comments down below if you want the other two as well. Leave a like, comment, share, subscribe, and thank you for watching.